this is Shiva. So in the last video we have seen the electric field due to an arc, right, at its axis, and we also seen the general cases. You would phi for the total phi as 2 pi, I'll get for the total ring, right, for the at its axis and also at its center we have seen. So if I take another similar thing, but instead of a line, now I take a 2D object, that is annular sector, right. So this is the one where our inner radius is r1 and outer radius is r2, right, and surface charge density I took it as sigma, right. So here instead of taking an element, right, I have considered an aerial element, right, not a line element, aerial element, and I've considered small charge due to this aerial element, and I took small dE and then integrated the total from r1 to r2. But since we are taking on the axis, right, again since this makes an angle here, it will have again two components, dE cos alpha and dE sin alpha. So it is alpha here and this is dE here, so this component will be dE cos alpha and this is dE sin alpha. So dE cos alpha first I've done, so dE cos alpha, so k small dq for this element, kq, divided by the distance from this element to the considered point, right, this one, square of this one, right. So that's why I've written here k dq into cos alpha. Cos alpha from this triangle, cos alpha is adjacent by hypotenuse, so that's why I've written x by hypotenuse, right. So dq, by the way, this one I can write as sigma dA, right. So sigma dA is r phi dr, and dA, right, length into breadth, small aerial element length. So aerial element thickness is dr, and the length of this one would be, length of the arc would be r into radius into the angle subtended by the arc, that is r phi. So that's what I've written here, r phi dr. So dA is r phi dr, and dq, the total would be sigma r phi dr, so that's what I've written here, right. After this so I computed this integral. So x square plus r square of written as t square. X is constant, considered point is constant, right, here x is not changing. The aerial element, it is going from here to here, r1 to r2, so aerial element is only changing, so r is changing from r1 to r2, so r is the variable, so that's why I've written 2r dr is equals to 2t dt, so r dr is equals to t dt. So k sigma x phi into integral, instead of r dr I have written t dt, right, divided by t cube. By the way, this is x square plus r square is t square, square square will cancel out, which gives us t cube. So 1 by t square, integral of that minus 1 by t. So k sigma x phi, instead of minus I've changed the limits, the same thing I did previous also, right. So if I continue on that, I've substituted the limits, right, r1 square and r2 square, so this is the general result we get, right, towards the axis, by the way, and this is for annular sector on its axis. For a complete annular ring, the angle subtended, right, here the angle is phi. If I take the complete ring, so this angle would be the total 360 degrees circle here, right, for the complete annular ring. So the angle subtended center would be 360 degrees, that is 2 pi. So instead of phi I took 2 pi here, and I got this result, right. So we get the same result by changing the limits if we do for the disk, right. For the disk also we approach with the same procedure, that is, we take the aerial element and substitute dq, and there we take limits 0 to r, because it is complete continuous 2D body, but here there is only mass present from r1 to r2, so instead of 0 to r, here we take limits r1 to r2, right. So from the disk one also we can do this one, right. So this is the x component. So as for the y component, that is d sine alpha, right. So I've done that also. DE sine alpha, same approach, excuse me, same approach. And yeah, the only small thing that I've taken or which was different is, so there I mean, if for the cos alpha term here, dq I've taken sigma r5 dr, that is sigma into dA is length of this one into this thickness, right? Length of this one I've took it as r5. But here, while considering dA sine alpha thing, I've considered with sine term actually, right? So up to here sine 5 by 2, I mean if I take this as not an arc but as a straight line, so if I apply sine 5 by 2 here, right, that is opposite one, that is this length divided by r, that's what I've written here. This is semi length, so semi length I get as r sine 5 by 2, I get the total. So if I take this symmetrical, this length would be equal to this one, so the total length would be 2r sine 5 by 2. So instead of just r5, right, this does make sense. I mean, if phi is very small, I can write as just sine theta is almost equal to theta, so 5 by 2, 2 cancels out, so this becomes r5. This is almost equal. But here consider this one, right, along with sine, and yeah, there's a sine term here, so sine 5 by 2, sine 5 by 2, although it's constant, right, so I can write, so continue that integral over here, right, 2k sigma sine 5 by 2 integral r square dr upon x square plus r square whole power 3 by 2. So 2k sigma sine 5 by 2. So again now from the triangle I took tan alpha as r by x, so r is equals to x tan alpha. This integral, it's a bit lengthy, but nevertheless it's doable. So x square r square term, x square tan square alpha, and dr is x secant square alpha d alpha, right? So I substitute that here, and yeah, x terms cancels out. So what will be the remaining is, so in the numerator we got tan square alpha and denominator secant alpha. Tan square alpha I can write as secant square alpha minus 1, right? That is secant alpha minus cos alpha. So instead of integrated each term, so integral secant alpha, that is natural logarithm tan alpha plus secant alpha, and integral cos alpha minus sine alpha, right? Sorry, not cos is just sine, there's a minus here, right? So tan alpha again, since we took this one, so this condition, so from the triangle initially, so I can write this one. So from this triangle thing, the trigonometric ratios I've written again in terms of r and x, right? So yeah, while integrating this one, usually we write plus c, so and this one ln, this directly I can write as r plus root of x square plus r square divided by x. So ln a by b, ln a minus ln b, so I've written minus ln 1 by x, that's, I mean, since x is from the considered point, this distance is a constant, right? So since that distance is a constant, ln 1 by x is also constant, that I've included in plus c, right? So yeah, this is the expression we got, and I've substituted limits from r1 to r2, and I've written this one. So this is one we got. This is a y component, and if we take the point as the center exactly, x becomes 0, right? X becomes 0 at the center. So Ey becomes this much at the center for the annular sector, 2k sigma sine 5 by 2 natural logarithm r2 by r. The approach is very much similar to the previous one, that is for an arc, right, on the axis. To be frankly speaking, the arc is more difficult, since there is a projection of projection we have to take into the account. But this one is a bit straightforward. Here, since we are directly taking aerial element, we don't have to consider that cos theta. So directly you can resolve this cos alpha and sin alpha, and directly we can integrate this. So I hope you got the point here, how we do this, and I will see you in the next video with another continuous body. Thank you very much.